Hello everyone, welcome to the mathematical session on foundations of algebraic structures and number theory. In today's discussion we are going to talk about the benefits and the applications of Wilson's theorem. So it could be considered as a continuation of my previous discussion on Wilson's theorem. So this particular theorem, the proof of this theorem leverages properties of factorials and modular inverses, because the concept of modular inverses is involved in the structure, because we are into we come across group, we come across field where we come across the property of inverse, so which is the beginner, where these concepts then next brought into the concept of number system. So the Wilson's theorem plays a very important role, as I told in the previous video, that it is a very important theorem. It's a key theorem, it's a fundamental theorem. While we discuss about prime number and congruence between the integers with the modular arithmetic concept, where prime number plays a very important role. So as an application of Wilson's theorem, we can say like Wilson's theorem aids more on cryptography, that is it is primarily it is used in testing areas. In testing areas we can use Wilson's theorem, but even Wilson's theorem has its own limitations. So calculating factorials of large values, for example here we talk about prime numbers. So calculating factorials for prime numbers, large prime numbers, makes this impractical to work. So that is the limitation of Wilson's theorem. But in practical usage, if you see, it is of more use, it is of more benefits, but there is obviously there will be some limitation. So as you know, the concept of Wilson's theorem says that if there is a prime number, then you can have a congruence relation, that is p minus 1 factorial is congruent to minus 1 mod p. So in which the factorial concept is involved more. But the thing is, if the prime number is a big number, if it is a very big number, then factorial concept goes as a tough one here. So it becomes impractical for huge values, huge prime values. Then if you want to practice, if you want to understand Wilson's theorem, you have to do more problems in Wilson's theorem. That is, you have to understand how to verify Wilson's theorem. Then you can go with small prime numbers. You can go with small prime numbers like 2, 3, then 5 like prime numbers, so that you can understand the fundamental of it. So when you use smaller versions of prime numbers, you can easily understand, grab the idea behind what Wilson is trying to say. And an application of Wilson's theorem, we can say Wilson's theorem is used to determine if a number is prime. So even it plays a wonderful role to understand whether the given number is a prime number or a composite number. So I would like you to tell you, like, you can take smaller prime values and you can understand, you can apply it in the Wilson's theorem statement concept, and you can derive solutions and you can understand so how it is useful in determining if a number is prime or not, so that you can have a very clear picture into that, and you can move to the next important theorems of this ideas of this prime congruence concepts. So I would like to talk more on Fermat's little theorem in the coming classes. Fermat's little theorem is again one of the important theorem related with congruence and prime number theory. So again it plays with prime numbers and the concept of congruence, where the concept of relatively prime, the idea is used between the integers taken for calculation and the prime number involved in it. So I would like you to concentrate more on Wilson's theorem to understand the best benefits of it, and also you can come into Fermat's little theorem where you can leverage more into the congruence ideas, so which is more beneficial and more useful when it comes to the concept of understanding and applying or working on algorithms of cryptography. So thank you for listening to this session. In the next video we will discuss Fermat's little theorem.